When do we have a left inverse? Yes, if you have a full rank tall matrix, then you have a left inverse C such that this is equal to, if A belongs to P cross Q, what is the size of Q? Sorry, size of I, or P cross P. It'll be Q cross Q. Okay. See, whether you have a left inverse or the right inverse, the identity matrix that you get will always have the smaller dimension. Here, this is tall, that means Q is smaller than P. Okay, and we also found out that there are infinitely many left inverses. For example, you can always find a C cap, gives you IQ, and C cap into A is simply the zero matrix. Q cross Q, zero matrix. Okay. And we saw if you have a linear system of equations like this, where you have a tall A, this might not always be solvable. This is solvable only if B belongs to the column space of A. It's not solvable if B. When this is solvable, then if you take any left inverse, right, and you multiply B by the left inverse of A, then you'll get the solution. Okay? And if B is not in this column space of A, then what happens? Well, you can still do this, but what you're not guaranteed is if B is in the column space of A, then this will be equal. If it's not in the column space of A, then it will not be equal. Okay. All right. That's all I wanted to say about left inverses. We will now move on to right inverse. Same idea. If you have A that is rectangular and full rank, but this time it's a fat matrix. Okay. Then you can always find a matrix B of size Q cross P such that this is equal to what now? IP or IQ? IP, yes. Again, there are infinitely many. Okay, where A times B cap is simply 0. P cross P. I mean, exactly the same set of arguments as before. Okay, except now everything is on the inverse is on the right side. Okay, so it turns out you can again the right inverses are useful in solving linear equations, but linear equations of this form. What can we say about the solutions of this linear equation if A is full rank? A is full rank and fat. We don't need to, okay. If it's square, it's unique. If it's fat but still full rank, yes. Is that the only possibility? Yeah, P is less. No, here P is less than Q. It's full rank. That means the rank is P. Okay. The only possibility is this. Okay. It turns out because there are infinitely many solutions, right? You can actually solve this, and you can obtain a solution for x by simply taking B and multiplying it by one of the right inverses. Okay. If you multiply B by any right inverse, you get a solution for this set of equations. Because there are infinitely many solutions here and there are infinitely many right inverses, you simply take all possible right inverses, post multiply by B, that will give you all possible solutions for this. Okay. In fact, in this particular case, if you take A and multiply it by it will always be equal. Okay. All right. Now, before we move on, this couple of things I want you guys to note. Okay. So we have we have this is always 0. We choose B cap such that this is always 0, and this is the way it's written here, right? In fact, this is equal to. If that is the case, okay, if you consider this, what can we say about the rows of A and the columns of B? Or what can we say about the columns of B if A times B cap is 0? Right? So this is A, and then your B is like this, right? It's got set of columns, and if you multiply them all out, you get all zeros. Exactly. What is orthogonal? You'll have to be louder. I can't hear you. Hey, we've not talked about a matrix being orthogonal to something, another matrix, right? We only talked about vectors being orthogonal to other vectors or subspaces being orthogonal to other subspaces. You're right. It has to do with something with orthogonality, but what are orthogonal? Transpose of what? Or here. Fine. Okay. Another clue. There are different ways to view matrix multiplication, right? What is the inner product view? Yes, the ijth element is simply the inner product of the ith row of this matrix and the jth column of this matrix. That is 0. In fact, all of them are 0. What does it say? What? No. I can choose I and j to be whatever I want, right? See here, the ijth element here, I don't know what to call this. I'll call it matrix D. Dij is 0, no matter what ij I choose. Right? Dij is an element that is obtained by taking the inner product of the ith row and the jth column. This simply means all the rows of this matrix are orthogonal to the columns of this matrix. Right? Or that is if you take the inner product view. If you take the column view, this is the product. The columns of the product are related to the columns of this matrix, right? If you do C equals AB, we learned that the columns of C are linear combination of columns of A, and the exact mixture is given by the columns of B, right? Here, this first column is nothing but this matrix multiplied by this column. The second column here is this matrix multiplied by second column, and so on and so forth. If a matrix multiplied by a column gives you the zero vector, this vector must be in the null space of this matrix. Okay, so your B cap, the columns of B cap are essentially elements from the null space of A. Okay, the elements in the null space are orthogonal to the rows of A, right? So that's also stated in this, right? If you take the inner product of the rows with the columns, they get 0. Okay. So here the columns are from null space of A. What about this? Turns out the columns of this are from the row space of A. What about here? So we had CA equals I and C cap of A equals 0. in this case, I'll just state it. You can think about why it is. The rows of C cap are from the left null space. Okay, and here rows are from column space. See, if that's confusing, just remember this picture. A transpose, CFA, null space of A transpose. Okay. Right. So that's a very brief discussion on left and right inverses. And we know that there are infinitely many, but there are some that are special, or there is at least one that is very special, which is called the pseudo inverse A. Pseudo inverse of a matrix A. Okay. There are two different expressions for the pseudo inverse. For tall matrix and for a fat matrix. The pseudo inverses are usually represented by a dagger. For a tall matrix, given by we'll first do the tall matrix and then we'll do the this is Q. What is the shape of a dagger? And a dagger A equals I Q. Okay. This is the left inverse. In fact, this is a very special left inverse of any tall matrix that has full rank. Again, we're only talking about full rank matrices. Okay, we're not talking about rank deficient matrices. This is called the pseudo inverse, or it's called the inverse. Inverse, and there might be other names as well. But whenever you see something like this, you know what they're talking about. Okay. So this is a special left inverse because see, whenever there are infinitely many choices, right, and you want to choose something from that infinite set using some criteria, okay, that's typically an optimization problem. You either want to maximize or minimize something, and choose an element that does that maximizes or minimizes something. Right? It turns out that the pseudo inverse is special because the pseudo inverse, right, is the matrix, or let me put it this way. The pseudo inverse is a left inverse of A, but if you do this, right, if you post multiply, right, you get a P cross P matrix. This P cross P matrix is a special matrix. This is in fact orthogonal projection matrix onto the column space of A. Okay. Earlier, if you remember, if we had a subspace and we had an orthonormal basis for the subspace U, well, let's say the columns of U form an orthonormal basis for the subspace U. What is the expression for the orthogonal projection matrix if you had an orthonormal basis? Remember this? Okay. This was an orthogonal projection, orthogonal projection matrix onto the subspace S. You can use this expression only if you had an orthonormal basis. If you did not have an orthonormal basis, what we had to do before was you take the basis, you do Gram-Schmidt orthogonalization, You find an orthonormal basis, and then you do UU transpose. If you don't want to do any of that, and if you had a matrix A whose columns span F, and you want to find the orthogonal projection matrix, then all you do is this. So essentially, this is equivalent to A transpose A inverse A transpose. These two are exactly the same. Given that the columns of U span S, the columns of A span S. Okay, yes, A was an orthogonal matrix, right? If the columns of A were an orthonormal basis for S, this will be I and this will disappear. So you'll get A transpose, exactly like this. Okay. In fact, what I've written down here, this is not the first time we are seeing this. We saw something like this earlier. Okay, it's just that the elements were not matrices before. You remember, if I have vector A, this is the subspace spanned by A. What is the orthogonal projection matrix onto the subspace spanned by A? A is not of length 1. What is the expression? The orthogonal projection matrix onto the subspace spanned by A. Louder. You have to be louder. I don't hear it properly. It's okay if you're wrong. It's all right. Yes. No, not A transpose. A? Huh? Yes. Yeah. Exactly. This is a scalar, right? I mean, I can do whatever I want with the scalar when I'm manipulating this vectors. I could have written it like this: A transpose A inverse A transpose. Because this is just a scalar. It's 1 divided by some number. If you look at the two of them, they're exactly the same. Right? So one way to make sense out of this, right? If you have an orthonormal basis, you simply do UU transpose and then you get an orthogonal projection matrix. But if the columns of A do not form an orthonormal basis, then of course you take the outer product, and then you have to do this. You have to include this term in the middle. Okay, what is the purpose of this term? Or what is the purpose of this term in this expression? If you had a single vector whose length was not 1. Yeah, it's just to normalize, right? This is just a normalizing term. Right? You're normalizing for the fact that A is not of length 1. Okay? If A was length 1, this disappears. Then you get A transpose only. That's exactly what is happening here. Right? Except now the A is a matrix. So the way to think about this matrix, what A transpose A inverse is really doing is it's doing two things, right? One, it's normalizing for the lengths of AI, the columns of A. Columns of A might not be of length 1. Okay, and two, accounting for AI and AJ not being orthogonal. That's all you're doing. Right? So that's essentially what is the meaning of this term that you have in the middle. Once you've accounted for the non-unit lengths of A and the fact that they are not perpendicular to each other, then this essentially is your orthogonal projection matrix. Okay, and you obtain A dagger as a solution to a minimization problem. We won't go into the details of the minimization problem. The solution. So, if you want to let's say we want to search, or actually let me call this C. C is possible left inverse of A. Okay, there are infinitely many of them, right? But what I want is I want to find a C such that if I do A times C into B and I compare this vector with this vector, I want to find a C that minimizes this whole thing. Okay, and it turns out if you minimize this problem, the solution that you get for C is essentially your A dagger. Okay, all right. So that's all I wanted to say about left pseudo inverse, which is basically an orthogonal. Well, A times the left pseudo inverse is an orthogonal projection matrix onto the column space of A. If you have a fat matrix, okay, and you have this, that's all. Say the transposes are the order of the elements is slightly different. Okay, and if you and what will be the size of this? This will be equals to, okay. We again know that there are and we know that A dagger will be. Yes. But we know there are many possible right inverses which could have given me IP. Okay. The special thing about this, right, is this. For example, we know that if you have a problem like this, right, where A is fat, full rank, there are infinitely many solutions for X, right? So I can obtain any one of those solutions by simply taking a possible right inverse. I can multiply it by B, and then I get a solution for this. Okay. Now, let's say we wanted to find a solution X that had the least second norm. Okay. Uh, there are infinitely many possible X's that will solve this. What if I wanted to find the X such that its second norm is as small as possible? Or it is the vector X that solves this problem. I want the shortest possible vector X that will solve this problem. So if you look to minimize this, right? Uh, but you're searching over all possible x's, but only those x's that solve this. This is called. You want to search over all possible x's that solve this equation, and you want to find the one that has the lowest length. Okay. If you solve this problem, what you get is your A dagger, and if you do A dagger B, the length of this vector will be less than any only the two norm. Okay. Any other possible solution where B is a right inverse of A. A dagger is just a special right inverse such that if you A dagger B will have the lowest length than any other right inverse multiplied by B in terms of the two norm. Now, we will look at the relationship between the this A dagger and the QRT composition. Okay. If you remember, if you have a tall A, full rank, and let's say A had a QR decomposition like this, A could be written like this. Okay. If A was square, right, and it had a QR decomposition that was QR, what was A inverse in terms of Q and R? Yeah. Do you remember? Must be in your notes. No, I think it's inverse. Q transpose, is that right? It's just this. Now we know A is QR. Okay, A is tall, full rank. That means we can do QR, and R will be a upper triangular matrix. This is E cross Q. This will be E cross Q, and this will be Q cross Q. Okay. Given that this is A is QR, tell me what is the left pseudo inverse in terms of the Q and R components, where we know the left pseudo inverse is this. Substitute for QR and then simplify and tell me what you get. So you essentially replace A by QR, A transpose by QR transpose. We simply substitute first. And then you first simplify this inside and then the inverse and then tell me what you get. What happens when you simplify inside? Ah, yes, this is transpose. You essentially first take the transpose inside. What will happen when you take the transpose inside the parenthesis? Here, yeah, yes, R transpose, okay, Q transpose, QR, right? Inverse, and this is R transpose, Q transpose. Okay, but this, what can we say about Q transpose Q? Not one, I, right? So this will disappear. So you're left with R transpose R inverse, R transpose Q transpose. What do we do here? It's inverse, no? So it won't be R transpose. What is AB inverse? Assuming that both A inverse and B inverse exist, this is simply B inverse A inverse, right? So this will be R inverse, R transpose inverse, R transpose, Q transpose. Here, these two will cancel out because this is the inverse of R transpose. So this goes off. So what you're left with here, if you have a tall matrix, right, full rank, the pseudo inverse has the same expression as if you had a square A. Okay? This whole thing will simplify to this. Right. Now let's consider the case where you have a fat A. A is A transpose A, A transpose inverse. Okay. Unfortunately, here A does not have a QR decomposition where R is upper triangular. Okay. Or you can tell me this. It's full rank. Okay. Let's assume the first P columns are linearly independent. Okay. You can still do the QR decomposition. A equals QR. This is P cross Q. This is what will be the shapes of these two matrices? We talked about this in the last class, or maybe the class before, or maybe last class. Yes, I simply mentioned it about the shapes of Q and R for different shapes of A. Okay? It will be like this. Okay. So what you will have is a square matrix that's orthogonal, and R will be like this. Okay. So R obviously does not have R inverse anymore. Okay. So it cannot be that expression. Okay. Earlier, in this case, right, R was square, upper triangular with no zero elements because this no zero elements along its diagonal. So you could take R inverse and R inverse exists. In this case, if you started with the full rank tall matrix. Okay. So this does not work. So we can't use this. But A is not, A is fat, but A transpose is tall, right? And full rank, right? If that is the case, then we can take the QR decomposition of A transpose. Okay. And let's assume the QR decomposition of A transpose is QR, not A. Because for a tall matrix, this is fine, right? Okay. If that is the case, now tell me what is, sorry, this is A. Tell me what is the right pseudo inverse of A in terms of Q and R. See, if A transpose has a QR decomposition like this, what is A in terms of Q and R? Not inverse. Why is it inverse? Take R. Yes. That's all. Now use this in this expression and tell me what does it simplify to? What do you get? You get an R transpose here, then you should not have an R transpose. So you get QR. So what is this? This will be I. Okay, so this will disappear. So you have R transpose R inverse. R is square, remember, and upper triangular with no zero elements along its diagonal, so it's invertible. So you can take the inverse inside. So you reverse the order, or well, this is actually R transpose inverse. Often we will write R transpose inverse as simply R minus T. Okay. So this is out because these two cancel out each other. So you have R, where Q and R are the matrices that are the QR decomposition of not A but A transpose. Okay. Okay, that's all I wanted to say about the relationship between the pseudo inverses and the QRT composition. We will now look at we won't talk about how to find a generalized inverse. We will talk about it later on when we look at singular value decomposition. But we'll at least discuss what does it mean when we're talking about inverses for rank deficient matrices. That's generalized inverses. These are inverses for rank deficient matrices. Okay? It means we have A. Now it does not matter whether it's square, rectangular. It doesn't matter. All that matters is we have a system like this. This is P cross Q, P cross Q, and the rank of A is R. R is less than minimum. There is again a slight difference whether it's tall or tall, fat or square. Okay, if A is tall and it's rank deficient. Okay, if it's full rank, then we know there are matrices C such that I get IQ, right? But this is not true anymore because it's rank deficient. But what you can get is you can find the C, and if you pre-multiply C by A, you don't get the identity matrix anymore. What you can get is this, a block matrix like this, identity matrix of size R, and then zeros of the appropriate size, where this is of size Q cross Q. Okay? You can only get IR, where R is the rank of the matrix. Similarly, if you have fat matrix, okay, you can find B, that again gives you IR 0, 0, 0. This belongs to only this is possible once you have rank deficient matrices. Okay. Let's look at what this means in terms of solving this equation. Earlier, when A was full rank and tall, there were only two possibilities: unique solution or no solution. When A was fat and full rank, there were infinitely many solutions. The moment you have a rank deficient A, now you always have infinitely many solutions if there is a solution. Okay, so if there is a solution, this implies there are infinitely many. Okay, the same thing applies if B is in the column space of A, then you have infinitely many solutions. If, of course, if B is not in the column space of A, this is not solvable again. And here again, like in the left and right inverse cases, there are infinitely many matrices that will, infinitely many left inverses and right inverses. Okay, but you can find, like we did in this, in the case of the pseudo inverses, we obtained the left and right pseudo inverse as solutions to an optimization problem. Right? For the left pseudo inverse, it was the matrix such that if you do A times C into B, that vector was as close as possible to B in terms of the two norm. In the right pseudo inverse case, we were looking at a pseudo inverse that gives you the x with the lowest two norm. You can find a similar situation here But now the issue is this, right? If B is in the span of A, then there are infinitely many solutions. But if B is not in the span of A, you can find an approximation for B in the column space of A, except now, because A is not full rank, there are infinitely many X's that will give you that approximation. Okay? So you can find something like the pseudo inverse. By now posing a minimization problem like this, where you're saying B minus, let's say A is tall, right? If A was full rank, this minimization problem would have given me the left pseudo inverse. Now, if you simply add this, right? So you want to find, if A is not, if A is rank deficient, then you still want to find a left inverse such that this projection is as small as possible, and you also want to find that C such that X, the solution that you get here, is as small as possible. Or this is essentially the okay. And later on, when we talk about SVD, we'll see how to find this matrix in terms of the SVD of a matrix, which will be something like this, and then we can simply find the inverse for a rank deficient matrix using just U, sigma, and B. We'll come to this later. Okay, that's all for matrix inverses. If there are any questions so far, we will discuss them now. Otherwise, we move on to the tutorial and then maybe discuss questions that you guys have for the assignments and stuff. Okay, all right. Then we move on to the maybe the questions that you guys have now for the assignments, and then we'll do the tutorial.